In this outcome, we move from single measurements to pairs and ask whether two things move together. We'll picture that with scatter graphs, measure it with correlation, and summarize it with a regression line. Up to now, we've studied one variable at a time. Bivariate Data records two measurements for each item, say the hours a student revised and the mark they scored. The question we keep asking is simple. As one goes up, does the other tend to follow? Correlation measures how strongly the two move together, and regression finds the straight line that best sums up that relationship. The scatter graph is always your first move. You plot each pair as a single dot, putting the independent variable, the one you think drives the change, along the x-axis, and the dependent variable, the outcome you measure, up the y-axis. With revision and marks, hours go across and marks go up. The shape of that cloud of dots tells you the direction and strength of any relationship before you calculate a single thing. Three basic patterns turn up. Positive correlation slopes upward. As x rises, y tends to rise too. Negative correlation slopes downward. As x rises, y tends to fall. And no correlation is just a shapeless scatter with no trend at all. On top of direction, there's strength. Points hugging a line are strongly correlated, a loose scatter is weak. The graph gives you that verdict at a glance. Let's put words to it. Positive correlation means both variables climb together, like revision hours and marks. Negative correlation means one climbs as the other falls. The classic example being price and quantity demanded. As price goes up, demand tends to drop. Strength is about how tightly the points hug a straight line, strong, moderate, or weak. And here we're only dealing with linear trends, roughly straight-line relationships. Now for the warning that never goes out of date. Correlation does not imply causation. A strong correlation only tells you two things move together, not that one causes the other. There might be a lurking third factor, a confounder, driving both, or with a small sample, it could be sheer coincidence. Only a carefully controlled study can pin down genuine cause and effect, so always flag that caution. Here's a favorite example. Across a year, ice cream sales and drowning incidents rise and fall almost in step, giving a strong positive correlation. Nobody sensible would say buying an ice cream makes you drown. The hidden third variable is hot weather, which pushes up both ice cream sales and the number of people swimming. That's a confounder, and it's a reminder that even a sky-high correlation needs a sensible explanation before you claim cause. In business, sales and advertising often both climb simply because it's the festive season. Once the scatter shows a linear trend, we can draw a straight line that captures it. By eye, you'd try to balance the dots above and below, but that's subjective. Ask 3 people, and you'll get 3 lines. So statisticians use the least squares regression line, the one unique line that makes the total squared vertical distance from the points as small as possible. That takes the guesswork out and gives everyone the same agreed line. We write the regression line of y on x as y equals a plus bx. The b is the gradient, telling you how much y changes for every 1 unit rise in x. The a is the y-intercept, the value of y when x is 0. Handily, the line always passes through the mean point, x bar, y bar. In practice, we work out b first, then use that mean point to pin down a. The gradient b is sxy over sxx. Now sxy is the sum of xy minus the sum of x times the sum of y all over n, and sxx is the sum of x squared minus the quantity sum of x squared over n. Once you've got b, the intercept a is simply y bar minus b times x bar. So in the end, you only need 4 totals from your data: the sum of x, the sum of y, the sum of x squared, and the sum of xy. The routine is 4 steps. Build a table with columns for xy, x squared, and xy, and total each one. Work out the means. X bar is the sum of x over n, and y bar is the sum of y over n. Compute sxx and sxy from those totals. Then finish with the gradient. B equals sxy over sxx, and the intercept, A equals y bar minus bx bar. Let's run real numbers. 10 students' revision hours as x and their test marks as y. We add columns for x squared and xy and total everything. That gives a sum of x of 65, a sum of y of 589, a sum of x squared of 505, and a sum of xy of 4269. The means come out at x bar equals 65 over 10, so 6.5 hours, and y bar equals 589 over 10, so 58.9 marks. Those 4 totals feed straight into the formulae. Now the coefficients. SXX is 505 minus 65 squared over 10, that's 505 minus 422.5, giving 82.5. SXY is 4269 minus 65 times 589 over 10, which is 4269 minus 3828.5, giving 440.5. So the gradient B is 440.5 divided by 82.5, about 534. And the intercept A is 58.9 minus 5.34 times 6.5, which works out at 24.19. Our regression line is y equals 24.19 plus 5.34x. Picture that line drawn through the scatter. It runs up through the mean point, 6.5 hours and 58.9 marks, and the dots sit nicely close to it, confirming a strong positive correlation. The beauty is that the line now lets us predict a mark for any number of revision hours we choose. And crucially, it's the objective least squares line, not somebody's hand-drawn guess. Let's translate those numbers into plain English. The gradient of 5.34 says each extra hour of revision is linked with roughly 5 more marks. The intercept of 24.19 predicts about 24 marks for a student who does no revision at all, though take that with a pinch of salt, since 0 hours may sit outside the data we actually collected. A positive gradient simply confirms the upward trend we saw on the scatter. Coefficients turn a picture into a precise, usable rule. Let's predict a mark for someone who revises 8 hours. We substitute x equals 8 into y equals 24.19 plus 5.34x. That's 24.19 plus 534 times 8, which is 24.19 plus 42.72, giving 66.9, so about 67 marks. Now 8 hours sits inside our data range of 2 to 11 hours, so this is interpolation and reasonably safe. Predicting for 40 hours would be extrapolation, way outside the data, and not to be trusted. That distinction is worth dwelling on. Interpolation means predicting inside the range of X values you collected, and if the correlation's strong, it's generally reliable, like our estimate for 8 revision hours. Extrapolation means predicting beyond that range, and it's risky because the trend may simply not continue. Revise for 40 hours, and the model happily predicts a mark well over 200, which is nonsense. Always check your prediction sits within the data you've actually got. One subtlety about which line we're fitting. The regression of y on x minimizes the vertical distances, treating y as the response we want to predict from x, so it's built to estimate y for a given x, not the other way round. Which variable you call x and which you call y depends on what you're trying to predict. Here we're predicting marks from revision hours, so hours is the explanatory variable and marks the response. Let's lay the symbols out plainly. The gradient b at 534 is the marks gained per extra revision hour. The intercept A at 2419 is the predicted mark for 0 revision. The y on its own is the predicted value, your estimated mark, for a chosen number of hours. And the mean point, X bar, Y bar is the point the line is guaranteed to pass through. A regression line is powerful but not bulletproof. It only fits a straight line trend, so a curved relationship needs a different model. It's sensitive to outliers. A single stray point can tilt the whole line. You can even fit a line to totally unrelated data, so always check the scatter and the correlation first. Extrapolating beyond your data can mislead badly, and, as ever, a fitted line still doesn't prove causation. The line is only as trustworthy as the data and the straight line assumption behind it. Let's take this into business. Imagine a retailer like Tesco logging weekly advertising spend as X and sales revenue as Y, both in thousands of pounds. The scatter shows a positive linear trend, so regression fits, and suppose the line comes out as sales equals 120 plus 4.5 times spend. That gradient of 4.5 suggests each extra £1,000 of advertising is linked with about £4,500 more in sales. Managers lean on that to plan budgets, but they treat the intercept and any extrapolation warily. And remember, season, price, and competitors all move sales too. Correlation still isn't proof of cause. So, to gather the outcome up, a scatter graph shows the direction and strength of a linear relationship. Correlation measures association only, never proof of cause, so watch for those confounders. The least squares regression line of y on x is y equals a plus bx, and it always passes through the mean point. The gradient b is sxy over sxx, and the intercept a is y bar minus bx bar. Use the line to interpolate safely inside your data and steer clear of extrapolating beyond it. That completes our tour of correlation and regression, from reading a scatter to fitting and interpreting the least squares line. To reinforce it, Crawshaw and Chambers sets out the coefficient formulae step by step, while Rowntree's Statistics Without Tears keeps the ideas intuitive, and Corbett Maths has clear worked videos if you'd like to see one built from scratch. The Royal Statistical Society's Significance magazine is a great place to see correlation used and misused in real reporting. Do dip into the Moodle ebooks for this unit and raise anything unclear with your tutor before the assignment.